Swayam Prabha. Digital India. Educated India.
Welcome back to the NPTEL course on Muffler Acoustics. This is week 4 and lecture 1. So, the objectives of this week's lecture, today's lecture, will be to understand what are the different metrics by which we understand the muffler is performing well or not, that is to say muffler is doing its required job or not. So, muffler performance metrics, that will be our goal, that will be our learning objective for today's lecture. So, how do you decide whether the muffler is performing nicely or not? So, we have 3 parameters, and in fact let me tell you something, these 3 parameters are not just very sacred to the muffler theory, but also in general these are used very widely in noise control engineering and in some way in different applications as well. So, these are insertion loss, also known as IL, measured in dB, everything is measured in dB. Transmission loss, also expressed or measured in decibel or dBA if you want to put the filtering thing, and finally level difference. Level difference is relatively lesser used quantity as compared to the above ones, LD. So, all of them are measured in dB, decibel. So, insertion loss, transmission loss, IL, TL and LD. We are going to understand, we are going to study what is meant by these 3 parameters, that is to say how the muffler theory is, how to evaluate the muffler performance based on these 3 parameters. Alright. So, before we go about doing that, let us or probably just review the different expressions used for evaluating the acoustic power. So, we know that if you have a duct and if you have say wave propagating along this direction and you have general say the pressure P tilde and U tilde, alright. So, we saw from I guess from the last week's lecture, week 3, the initial first or second lecture, I am not sure. So, we saw that the intensity is given by is real part of Z times U tilde RMS square, used very widely in electrical circuits. Z is an impedance of the medium, and another equivalent expression is P tilde RMS square by Z into cos theta. So, well, these are the 2 expressions that are used quite often, but then if we do not know what URMS is, what PRMS is in a directly in a upfront manner, theta of course being the phase between the pressure P tilde and U tilde, but an equally important representation that is used and from that we can derive a lot of expression is basically equals, let me write it in another slide, I is equal to half into real part of pressure P tilde acoustic pressure times U tilde star. So, here your U star, U tilde is the acoustic particle velocity, not the volume velocity, not the mass velocity, it is just the acoustic particle velocity U tilde. So, you get that from the Euler equation of course, and U, what does the star mean? What does this particular thing mean here? It means complex conjugate. So, P we get the solution in terms of complex exponential. So, U tilde star is the complex conjugate of U. So, let me make this thing clear here, U star is the complex conjugate of U star. that is what it is. So using this expression we can actually show this of course is equivalent to half into real part of P tilde star times U tilde, and you can keep manipulating to get different expressions. So we can actually show that the intensity for periodic signals over a given cycle can be expressed also in terms of, we remember 1 by T average was the thing, and 0 to T average, and since pressure is complex quantity, we will take the real part of P tilde into real part of U tilde times dt and integrate it. So P tilde is obviously ZU. So I mean if you simplify this thing further, you will get omega by 2 pi and 0 to 2 pi by omega times real part of ZU times real part of U tilde over dt. So, well, the point I am trying to make here is that when you do all the math, you will find the starred expression the same as this one, or probably triple star one. This is the same. So, the idea is that either we figure out the real part of pressure and velocity and integrate that and then find out the intensity, or simply multiplying, taking half of real part of P into U star complex conjugate will give us this. So, half happens because we are integrating over a period of time T average, which is nothing but 2 pi by omega, and the half factor actually comes because when you take the RMS you get 1 by root 2 and similarly 1 by root 2 for the velocity. So, the half factor is basically for the time thing. So, I mean it can be shown, I am not going into the details. So, once we get, basically the idea is to make use of either the double star or the triple star expression shown here for evaluating the muffler performance. We will probably use this one, and this thing then needs to be multiplied by the cross sectional area to get the acoustic power. So, we will use quite frequently acoustic power carried by a wave front as half into real part of P into U star complex conjugate. Now, if we multiply this by the density and divide by density rho naught, and then multiply this by cross sectional area and also divide the denominator by S, that is the cross sectional area. So, we are going to get the acoustic power, and so this obviously has to be multiplied by S further, because S is, we are trying to get this thing in terms of the mass velocity. So, basically this guy is the intensity and this is the area, cross section area. Well, we saw that the acoustic power carried by a wave front then is this thing. So, what we probably can do is that represent this guy here, we recognize that this, all these terms combinedly represents the acoustic mass velocity. So, we will simplify that eventually, and these thing and this thing cancel, because you know acoustic intensity times the area is your power. So, power carried by the wave front P I into S, and after a little bit of simplifications what we got is real part of pressure into the mass velocity complex conjugate, and in the denominator you have density, alright. So, this is what it is, real part of this thing. So, we are going to use this expression as well as some of the previous expressions for evaluating the muffler performance, insertion loss or transmission loss. Especially this is the one that I guess we will be making use of, and another one especially for doing the TL calculations, and also these two ones for basically the insertion loss. Actually, this can be simplified once we recognize that P RMS is nothing but 1 by root 2 times the amplitude. So, once we do that, we get this. Similarly, we can also get for this one half times real part of impedance times u u square, and here denominator can be density and s will be multiplied in the numerator to. So, this can be actually the mass velocity. The point is we will use these expressions for the insertion loss, and particularly this one for the transmission loss computation. So, with this background or recap of the acoustic power relations with pressure and velocity, I guess we are in a good position to talk about the insertion loss, the development of expressions for computing the insertion loss, transmission loss, and so on. So, let us begin with the IL first. So, what is IL? What is IL? So, insertion loss is defined as the acoustic power radiated without any filter and with the filter. So, it is the difference of the logarithm of the acoustic power that is radiated without the filter and when the filter is in place. So, basically this is your say the engine block, and we saw the slide a while back. So, this is just a thing with this. So, this is your engine block, or another representation can be perhaps this one. So, we see this is the engine which is making a lot of noise, and this is the exhaust system or the muffler system. Let us say this is not in place, or I would say this entire thing what we are seeing here, this is not there, only the engine is making noise and this is going away, and it is almost unbearable, because this without the muffler engine does produce a lot of noise, and that is why the mufflers are in place. So, then we decide to put the muffler on, that is you have all the complicated elements. It could be much more complicated things, and the noise emission is reduced. That is to say, now when you are standing here and listening, so now it is, you can manage, you can, it is still tolerable. So, basically then you say that, well, the muffler is doing its job, it is well designed muffler, and you are happy. So, how do you define that? What is the quantity? So, suppose when this was not there, and only this part was there, it was making a lot of noise. So, we will call this part as the LW1, that is basically the acoustic power. Remember, W was used to denote the acoustic power, and SPL was used to denote the sound pressure level. So, LW1 means when the muffler is, this thing is crossed out, it is not there. So, L1 is the acoustic power that is being emitted out and going off in the atmosphere without this thing. Now when you have got the muffler in place, the acoustic power comes out, the waves come out here, and you record this. Note that this LW1 is to be recorded at the same place. So, when the muffler is not there, then you record it at a certain distance from this thing, and when the muffler is there, you still should record the noise at this point, and then it is given by LW when the muffler is on. So, now basically the difference of the insertion loss then is defined as IL is equal to LW1 minus LW2. So, when the muffler is on, it produces certain power, and then when the muffler is not there, it is off, then it produces certain power LW1, and when the muffler is on, when it is put on, it is doing what it is supposed to do, then it produces a different sound acoustic power level, and that is given by LW2. So, the difference of that is called insertion loss, LW1 minus LW2. All right. This of course is in measured in dB. It may so turn out that for certain frequency spectrum, insertion losses is a significantly large quantity. That means in that frequency spectrum, the muffler is doing its job nicely, and in some frequency range, insertion loss can be actually negative also, which means that the muffler is counterproductive over that frequency, it is creating actually more noise. So, insertion loss, the point to be noted here is that the insertion loss can be negative also. So, basically IL is then given by LW1 minus LW2, and that is equal to 10 times log of W1 by W2 to the base 10, of course. So, because W was used to denote the acoustic power radiated. 1 and 2 means with and without the filter or the muffler. Filter means the muffler. Let me also clarify, muffler is defined, filter is defined as the muffler. All right. So, now we will make use of the expressions that we talked about. So, I guess we probably have to go back to the presentation and actually incidentally to the to this form and talk about the acoustic power radiated. So, when this guy is not there, we will use the pressure form or the Thevenin's form, and what is the acoustic power radiated when this guy is not there. So, that is, so when the muffler is not there, then the circuit just becomes P n plus 1 times, it goes like this, then there is a load here and it goes like this. All right. The point I am trying to make is that what is the current passing through that, or what is the mass velocity. That is simple to evaluate, P n plus 1 tilde divided by Z n plus 1 plus Z naught atmospheric impedance. So, that is your current or the acoustic velocity, V n plus 1 or V n. All right. So, that is what it is. Now, what is the power? Since we know this, so we just derived an expression for the acoustic power radiated or carried away by the wave fronts when you know the amplitude of the velocity. In terms of the acoustic mass velocity is given by 1 by 2 rho naught times P n plus 1 Z n plus 1 plus Z naught times square, and if you recall, it is a real part, it is a real part of the impedance. So, this is the velocity. V is something like, the factor of 2 comes because of the RMS sign, 1 by root 2 multiplied by 1 by root 2, and rho naught is the density because we are working with a mass velocity, and S of course will be intrinsic to that, it is multiplied, and we need to take the real part of the impedance. So, real part of the impedance means it is R01. So, R01. So, what does R01 means? R01 is the real component or the resistive component. Please keep reminding yourself, real component of the impedance is the resistance that is always going to dissipate the energy, or if you evaluate that over a cycle, it is always going to be non-zero if the real part or the resistive part is non-zero. Real component of the radiation impedance or the atmospheric impedance, radiation impedance Z naught 1. So, Z naught 1 is the same as Z naught. Well, we are just introducing terms like or terminologies like comma 1 basically to talk about the fact that the muffler is not there, and with 2 when the muffler is there, like I have been emphasizing on that. So, 1 by 2 rho naught times this thing, this is the acoustic power that is radiated when the muffler is not there, just radiated to the atmosphere, and it is a pretty simple thing then to know or to appreciate that when the muffler is there, we need to figure out the velocity that goes on. So, when the muffler is there, then let us say we need to make use of this form, we need to make use of the Norton's form to evaluate the velocity that goes on, that comes here. So, when using the Norton's form, we can evaluate the velocity that goes on in this part, and we can figure out, I just probably need to rub this part and figure out that when the muffler is there, then we use the Norton's form and to find out V naught, making use of the shunt impedance thing. We know Pn1 and we know the source impedance, source characteristics, which are Pn plus 1 and Zn plus 1, quite difficult to evaluate analytically or through, it has to be done through experiments. But if you want to find out, predict the insertion loss, you first need to know a priori what is the source characteristics. We are going to mention about that. So, Vn plus 1 is known because this is known, and now Vn plus 1 is this thing, and then Vn can also be figured out, because this thing gets split into this part and this part, and then from once we know Vn, we can evaluate V naught, and so that was actually done previously. So, what we probably can do now is to just simply make use of the expression of, once we know, assume the things are known in terms of V naught. So, the power that is radiated when the muffler is put in its place is 1 by 2 rho naught, or rho naught comma 2. Density, it means that the density of the exhaust gases when the muffler is there. So, rho naught comma 1 and rho naught comma 2 might be slightly different based on the temperature of the exhaust gases, but we can assume them to be the same for just for simplifying our analysis, and this is square times R naught 2. So, where again R naught 2 is the radiation impedance or the atmospheric impedance here when the muffler is in its place. So, write down the expression for the insertion loss, which is nothing but 10 times log to the base 10 times rho naught 2 by rho naught 1 R naught 2 times P n plus 1 by Z n plus 1 plus Z naught times square of that, and here we get this. So, we get this particular expression for the insertion loss. So, here we get this thing. I guess probably I was missing a term here. So, in the denominator we probably have your V naught square, and so once we simplify this expression, what we are going to get is I L is nothing but 20 times log to the base 10 rho naught 2 R naught 1 rho naught 1 R naught 2. So, this entire thing is to the power half, that is square root of this, and now this is an interesting expression, Z n plus 1 divided by Z n plus 1 plus Z naught comma 1 and V n plus 1 by V naught. So, this is square was if you recall, I mean this, there was a square here. So, we are taking the square there, and but the important thing is that P n plus 1 has been replaced here in this expression by Z n plus 1 times this thing. So, this is what we did. So, we replaced this thing using the velocity representation or the Norton's form. This was possible using that, we made use of Norton's representation. So, the speciality or the peculiar thing about this expression is that it relates the insertion loss in terms of what is popularly known in classical muffler analysis as the velocity ratio. So, V n plus 1 is the velocity, acoustic mass velocity right at the upstream. So, V n plus 1. So, suppose if you have, no matter how complicated muffler you have, all you need to do is that find out the ratio of V n plus 1 and V naught. These things, once you can evaluate that using some analytical planar wave modeling, we are going to do that in ensuing lectures. Then I guess one can easily figure out the insertion loss. So, what we need to do is that we need to know, often this assume that rho naught 2 is equal to rho naught 1 and S on radiation impedance with and without the muffler are assumed to be the same. We can assume that without too much of, without making the system too complicated. So, as a result what happens is that this entire terms is evaluated to be 1, and insertion loss can simply be written as 20 log to the base 10 Z n plus 1 pi Z n plus 1 plus Z naught times V n plus 1 tilde by V naught and like this. So, this is what we are going to get, and this is called, this is known as V R n, V R n plus 1 or simply V R, which is the velocity ratio. So, now in the hypothetical case where you have 0 temperature gradient. I am saying hypothetical because, well, as the hot gases flow throughout out of the exhaust system, its temperature drops, but for most of the analysis in muffler is carried out for 0 temperature gradient. We assume a constant or uniform sound speed. If you recall, sound speed was root over r gamma times r naught into temperature in the absolute Kelvin scale. So, for hotter gases sound speed is increased, and for as the gases cool down towards the tailpipe, its temperature reduces, and so does the sound speed. It is directly proportional to square root T. So, but of course, lot of analysis assume a constant sound speed. So, that is what in fact we are going to do in this course without complicating matters. And area S, and we often assume that the cross section area of the exhaust pipe and the tail pipe are the same. So, with all these assumptions, it can be shown that if you have these things and a constant pressure source. So, for a constant pressure source, basically you have the impedance, source impedance tends to 0. Why? Why does this thing? Because if you recall, it was P n plus 1 times Z n plus 1 plus Z naught without the filter. So, when this term tends to 0, the source impedance tends to 0. So, under such a condition, we can still combine Z n plus 1 and V n plus 1, and this term can be combined here. So, basically what happens is that the insertion loss becomes 20 log to the base 10, and we combine this thing term together to get P n plus 1 tilde, and ignore this term because this tending to 0, and V naught into Z naught is nothing but P naught, the atmospheric pressure, and this is what we are going to get. So, in fact, we will see, and this actually can be written in yet another manner, which is nothing great about it, is just another representation, the square one of course, square times. So, basically for a constant pressure source, that is if the source impedance is 0, if we just measure the acoustic pressure without the muffler on and with the muffler on at a given location, so P n plus 1 and P naught, and well, let's take this ratio. So, we are going to get the, actually this will be n, I am so sorry. So, then we are going to get the insertion loss, and this will be shown to be equal to the level difference in the limiting case. Actually, another thing is that if the source impedance, in this case insertion loss will be equal to level difference, which I am going to talk about soon, and transmission loss is yet another quantity. So, before we will probably talk about TL and LD in the next lecture, lecture 2 of week 4, but one thing, a couple of comments about insertion loss is that unlike transmission loss, insertion loss is easier to measure. Basically, as we will soon appreciate, is for insertion loss we just need to measure the pressure without the muffler on at a given location, put the muffler on and measure the pressure again at that point, and then taking the ratio of that for a constant pressure thing, we can evaluate, we can actually experimentally get the insertion loss. However, experimentally measured IL in dB or dBA. However, if we were to analytically or well predict through some numerical finite element scheme, once we know the characteristics of the muffler, if we can relate the upstream and downstream variable through some numerical modeling and well evaluate the 4 pole parameters, we will talk about that sometime later. And once we know that and we want to evaluate the insertion loss through some numerical scheme, predict that, then it is a much more complex task for the simple reason because we need to know the source characteristics P n plus 1 and Z n plus 1 or Ps Zs. So, if we basically want to start from the analytical principles or some numerical thing, not only we need to do the muffler wave propagation modeling within the muffler, we also need to evaluate or know the source impedance and the source pressure. Fortunately, lot of work has been done in this field, and there are some empirical expressions that are well known to us, which we can use in the codes to numerically predict the insertion loss. So, another quantity is the transmission loss, which will turn out that it is much more difficult to experimentally measure compared to insertion loss, but easier to predict using set of routines, analytical modeling or numerical FE based modeling and so on. It is best that we talk about TL and possibly about LD, level difference, in the next lecture. So, next is the transmission loss, what we are going to talk about in the next class, that is lecture 2 of week 4. So, stay tuned for that. Thanks.